In this video, I want to introduce the root test. The idea behind the root test is just like the idea behind the ratio test. In the ratio test, we looked at a limit as n goes to infinity of absolute value of an plus 1 over an. Here we're going to do the same thing, but instead we'll look at absolute value of an raised to the 1 over n power. So the nth root of absolute value of an. This works great when that nth root has a nice form. So if an is equal to something to the nth power, or to be more explicit, even a ratio of two things to the nth power, the root test works great. So let's look at this series, s equals sum from n equals 1 to infinity of 1 minus n over 2 plus 3n all to the n. This is in this second form. It's a ratio of things to the nth power. And the idea, before telling you exactly what the root test says, is let's look at L, which will be the limit as n goes to infinity of absolute value of an to the 1 over n. Well, what is that? It's a limit as n goes to infinity of, what is absolute value of an? It's 1 minus n over 2 plus 3n. Oh, this whole thing raised to the n first. To the n. Now we put in this absolute value, and we get a 1 over n. 2 plus 3n is always positive. 1 minus n, for n equals 1, it's 0. For n equals 2, it's negative. For any bigger n, it's also negative. So what does this absolute value do? Here, the numerator is less than or equal to 0. So the absolute value is just going to turn 1 minus n into n minus 1. So this is a limit as n goes to infinity of n minus 1 over 2 plus 3n, all raised to the nth power, and then raised to the 1 over n power. And if you have some number raised to the a power and then to the b power, what you're getting is something raised to the a times b power. So this is the same as the limit as n goes to infinity of n minus 1 over 2 plus 3n raised to the n raised to the 1 over n. That's the same as raising it to the n times 1 over n, which is 1. So we're just getting n minus 1 over, let me rewrite this as 3n plus 2. And what is this limit? We could factor out the highest power of n from the numerator. We get n, and from the denominator, we get n. And we'll get n over n cancels. We'll get something that goes to 1 as n goes to infinity divided by something that goes to 3 as n goes to infinity. This limit is 1/3. All right, well, what does that tell us? Just to get ahead of ourselves, because 1/3 is less than 1, that's going to say that S converges by the root test. So why is that? Well, what does the root test say? This statement looks just like the statement for the ratio test. So if L is less than 1, then S is absolutely convergent. Again, not only does the root test tell you that S converges, but that S converges when you replace an with absolute value of an. That makes sense because when we take this limit, we're putting in these absolute values. If L is bigger than 1, then S diverges. And if L is equal to 1, the test is inconclusive. And you have to try another test. So look, this statement is exactly like the statement for the ratio test. It's just that this L is now defined in a different way. Let me say one more thing here. In this case, that the test is inconclusive, you have to try another test. Don't try the ratio test. If the root test is inconclusive, the ratio test will also be inconclusive. If the ratio test gives L equals 1 and is inconclusive, the root test will also be inconclusive. So the ratio test and the root test kind of go together. So if one of them doesn't work, the other one isn't going to work either. So in the next video, we'll just do a few examples where we see whether or not a series converges by applying the root test.